Welcome. In this session, we'll learn the concept of this time constant in RL circuits. Let's start. So again, we are going to learn this time constant in RL circuits by using simulation, and the simulation software that we are going to use is Matlab. All right. So let's revise this RL time constant concept again very quickly. So we have a network. In this network, we have RLL, and to this network, we apply a source V of S, which is connected at t equal to 0 to this, and this is L, and our goal is to see what is the behavior of this inductor current, the current that flows in the circuit. And we saw in the previous sessions, I of t is simply V of S of by R, 1 minus e to the power of t by tau. Now tau is the time constant, and for RL network, it is given by L by R and has the units of seconds. All right. Now we saw the behavior of this inductor, this current. We know it looks like this. If this is the final value, that is Vs by R, and we saw the current rises like this. Means it reaches to the final value, that's V by R, almost in 5 time constants. Means it reaches approximately to the final value in 5 time constant. And what is time constant here? L by R. So if we take the simple example, if we say Vs is 1 volt, L is 1 and R is 1. Okay, L is 1 ohm Henry, R is 1 ohm. Then what will be the time constant? L by R, that's equal to 1 second. That means in 5 seconds, the inductor current should be approximately equal to Vs by R. Vs is 1, R is 1, that is 1 ampere. Means in 5 seconds, the inductor current should be almost equal to 1 ampere. All right. Now, same way, if I say L is now 0.5, R is 1, and V is again equal to 1. So what will be the time constant here? Time constant will be simply 0.5 divided by 1, that is 0.5 seconds. So that means in 2.5 seconds, that's equal to 5 tau. 5 tau will be equal to this, that is 2.5 seconds. I of t should rise to 1 ampere. All right, this is the concept of this time constant. All right, we say in 5 time constant, the inductor current rises to the final value. All right, I hope you have got that. Now, if Vs is 10, L is 1 Henry, R is 1 ohm. How much is time constant? Time constant is again L by R, that's equal to 1 second. So that says in 5 tau, how much is 5 tau for this special case? It's equal to 5 seconds. So in 5 seconds, the inductor current should rise approximately equal to 10 amperes. All right, let's check this behavior using the simulation. All right, okay, one more thing before we do that. Now, what's the behavior of the inductor voltage? See, if this is the inductor voltage, we know the inductor current and inductor voltage are related by this. V is equal to L di by dt, where I is the current flowing through the inductor, V is the voltage across the inductor. So what's this VL equal to here? So V of t will be equal to L, and I is this, differentiating this expression, it will be Vs by R. 1 differentiation of 1 is 0 minus e to the power t by tau, and it will be minus 1 by tau, and this will be simply L by R Vs by tau e to the power of minus t by tau. Now if you substitute the value of tau here, it will be simply Vs e to the power of minus t by tau, because tau is L by R. L and R will get cancelled with that, so we are left with this. So V of L is equal to Vs e to the power of minus t by tau. All right, Now, what is the value of the inductor current at t equal to 0? That is 0. What's the value of the inductor voltage at t equal to 0? That's equal to Vs from this expression. Have a look. I of 0 is 0 from this expression. VL of 0 is Vs from this expression. Have a look. What does it say? If the current, when you connected this switch to this in the circuit, is equal to 0, that means there is no drop across this, right? All the voltage is appearing across. When will be the current 0? When inductor is behaving like an open circuit. So all the voltage appears across this inductor there, as the inductor behaves as an open circuit. So at t equal to 0, when you connect the switch in this RL circuit, the inductor is behaving as an open circuit. Open. So when you connected the switch with this, inductor behaves as an open circuit. This is very, very important for an RL circuit. All right. So let's observe the behavior of this inductor current and inductor voltage in this RL network using Matlab software. All right. Let me switch to Matlab. Let me share the screen with you. So this is Matlab. Now let me open Simulink. Again, don't worry about the components that I'm going to use. Just pay attention to the three components. That's the voltage source, inductor, and resistor that we will use in this. All right. The rest you can forget. What are the different components that we use here? Okay, let me bring a voltage source. So this is the source that we are going to use. Then we'll use a resistor. So this is the resistor. Then we are going to use an inductor. So this is the inductor. And since we have to measure the current also, so I'm going to use a current sensor here that will give us the current that flows in this inductor. All right, so this I'm going to connect here this, and this I'm going to name as I of L, means the inductor current. All right, so this okay, this is inductor current. And let's change the values. So let's assume we are using a DC source of value 1. So this is the value of the voltage source. Then the value of the resistance we are going to take as 1 ohm. It's already 1. Then the value of inductance is simply 1 Henry. So apply. And this, let's simulate it. Okay. Let's simulate the inductor current. Okay, what's my voltage value? Voltage value is 1. What's the value of resistance? 1. What's the value of this inductance? 1. So the time constant for this circuit is equal to 1. All right, let's see the plot now. So inductor current should reach to Vs by R. How much is Vs by R? 1 ampere. So it should reach to 1 ampere in 5 time constant. 5 time constant is equal to 5 seconds here. Have a look. In 5 seconds, it approximately reaches to the final value. Maybe it's equal to 1 ampere here. All right, it reaches to this. All right, now let me go back and okay, so let's change the inductance value. Let's change it to, let me go back. Let me show you that. So inductance value is now 0.5. All right, so let us switch to this. So now the time constant is equal to, means tau is equal to 0.5 seconds. So now you can see the inductor current reaches to in 2.5 seconds. That's equal to 5 tau for this circuit when R is equal to 1, L is equal to 0.5. So it reaches to 1 ampere in this. All right. Now let's change the value of this inductance back to 1. And let's suppose the value of the DC source is 1. So what is the final value of the current? It is 10 amperes because R is equal to 1. So it will be Vs by R, that's equal to 1 ampere. Sorry, 10 ampere. And let me show you the plot. Now the time constant again is equal to 1. Have a look. In 5 time constant, it reaches approximately equal to 10 amperes. All right. Now let me change back the value of the inductance back to 0.5. Let's see what will happen to this inductor current. All right. So let's switch back to this. Have a look. Now it should reach to this 10 ampere in 2.5 seconds only. Have a look. It is doing that. All right. Now let's measure the inductor current also. Okay. Sorry, voltage this time. Let's measure the inductor voltage also. All right. So let us use Mux here. So let's do that. So let me use this. Let's call it V of L of L. Okay, let's switch back the values. So it's equal to 1. And the input voltage is 10. R is 1. Inductance is 1. Okay, inductance is 1. So what is the final value? Vs by R. Vs is 10, R is 1. So that's equal to 10 ampere. All right, let's go back and see the plot. Let's go back and see the plot and have a look. In 5 seconds, it should reach to this 10 amperes. Have a look at this. And inductor voltage. Okay, let me mark the axis as well. So this is I of L. And let's display the legend as well. Have a look. IL means the inductor current rises to the 10 amperes in 5 seconds, and inductor voltage approximately decreases to 0 in 5 seconds. All right. I hope you have got the idea. I hope this is visible. Let me share the screen again. So you have a look at this. When R is 1, L is 1, and input is 10 volts. So the final value of the current will be 10 amperes. So inductor current should rise in 5 seconds to this 10 ampere current, and it should drop to 0 in 5 seconds. All right. I hope you have got the idea from this. All right. Okay, let me end this session here. This is the simulation of the time constant in RL network. All right. Let me end this session here.